back to Team Adams Teaching. This time we are looking at using scientific notation. Last episode we saw how to write numbers in scientific notation and transfer or go back and forth between standard notation and scientific notation. Now we're actually going to use those numbers to do something. There's two different ways to do this. One could be you work in standard notation. And so on this one, you're going to take all the numbers you're given and change them into a standard form. Then you're going to perform the calculation like you normally would, and then you're going to convert it back to scientific. Wow, that's not how you spell it. Scientific notation. And so our first example, 2.4 times 10 to the 5th power times the quantity of 6 times 10 to the 9th power. First off, if we want to make this into a standard notation or standard form, I would take this decimal point and move it back 5 places to make it a larger number. 4, 1, 2, 3, 4, 5. Notice the decimal point was here, and now if I move it back 5 places, it'll be there. So 240,000. And then we're going to multiply that by 6, and the decimal point was here. We're going to move it back 9 places. 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we get 6 billion. So what we could do, go ahead and multiply those together. What we'll do is I'm going to do 24 times 6, which is 144. And then there's 9 zeros here, and then over here, 4 more. So that is our total of 13. Yes. Okay. So I'm going to add 13 zeros to the end of this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's a lot of zeros. I'm going to put my commas in so we can see what kind of number this is. Let's see, comma every 3. And there we go. There's my awesome answer. But if I want the answer in scientific notation, now I have to rewrite it like that. That's going to be 1.44 times 10 to the, it's a big number, it's going to be a positive exponent. Decimal point was here, but I move it over here. So 3, 6, 9, 12, 15. I moved it 15 places over, and there's my answer. Okay. So that's one of the ways that you'll always get the right answer, but it's got a lot of zeros, a lot of big numbers involved. It's going to seem easier on the second way, but there's a little hiccup to it at some point. So here it is. If you want to use the other way, we've got using exponent rules. You can just group like factors. For example, if it was 8 times 10 to the 4th power divided by 4 times 10 to the negative 3rd power, I'm going to group the 8 and the 4 and the 10s and their exponents. I'm going to calculate using exponent rules. So remember, numbers act like numbers. They always have. 8 divided by 4 is 2. Times 10 to the, and when you are supposed to divide bases with exponents, you actually subtract them. And so this would be 10 to the 4 minus the negative 3rd power. Remember, subtracting a negative is the same as adding. So really we have 2 times 10 to the 7th power. And that's our answer using exponent rules. You can see that one's a lot quicker than the first step, but sometimes something kind of tricky happens. And so here's what happens a lot of times when you do use exponent rules. So 2.4 times 10 to the 5th power times a quantity of 6 times 10 to the 9th power, same as the one above it. And so what we'll do is we'll start by multiplying our 2.4 and our 6. And when we get that, we get 14.4. And then we have to use our exponent rules for 10 to the 5th power times 10 to the 9th power. And you're supposed to be multiplying bases with exponents. You actually add the exponents, 9 and 5, that gives us 14. So it looks like we've got the answer. However, this is not in scientific notation. If you remember, the digit here has to be between 1 and 10, less than 10 and 1 or larger, and it's not. It's 14, bigger than 10. So this part is technically not in scientific notation. So what I'm going to do, I'm going to rewrite just this part here. If I want to make this into scientific notation, I have to move the decimal point back 1 place. That's 1.44 times 10. And now I moved it back 1 place, so that's the first power. What you'll notice is if you multiply 1.44 times 10, you get back to 14.4. So this is the same thing as this. But don't forget, we still have this piece here. It needs to get rewritten times 10 to the 14th power. So this didn't go away. We just now need to combine it with the whole, and that gives us 1.44 times 10 to the, when you're multiplying bases with exponents, you actually add the exponents. That gives us the 15. You'll notice this is the same answer as we had for the first problem because it's the same problem. So that's two different ways to solve it. So let's actually try those out now on some problems. All right, so our first one here, the average distance from the sun to the earth is 1.488 times 10 to the 11th meters. If the length of the average paperclip is 3 times 10 to the -2 meters, how many paperclips would need to be connected together to reach the sun? So we're going to break the big, huge distance of the length from Earth to sun, and it's going to be split into little tiny paperclips the whole way. So we're going to actually split them into pieces, which is dividing. So I need to take these two and divide them. So 1.488 times 10 to the 11th power divided by 3 times 10 to the -2 power. I'm going to use exponent rules. I think it's a little faster. I'm going to group these together. If I do 1.488 divided by 3, I get 0.496 times 10. And if I group these together, when I'm supposed to be dividing bases with exponents, I actually subtract the exponents. It's going to be 11 minus -2, which is the same as 11 plus 2, or 13. So it appears we're done. However, once again, that's not in scientific notation. So I'm going to rewrite just that one little piece of my answer in scientific notation. I'm going to move the decimal point to after the 4.96 times 10. And then I had to move this decimal point back this way. So it's going to be to the -1st power. And notice that if I take this number and divide it by 10, I get this number. So this is the same thing as this. But don't leave this part off. That still is part of the answer. So now if I group these together, I get 4.96 times 10 to the, and when we're multiplying bases with exponents, we actually add them. -1 plus 13 is 12. And there's my answer. That many paper clips. That's a lot of paper clips. All right. Ooh, food. And most likely potatoes? Potato chips. Okay. The United States Department of Agriculture reported in Vegetables and Melons Outlook in 2007 that the average American consumes about 7.4 times 10 to the 1st power potato chips in a year. Oh, sorry, to the 3rd power. I misread that. Since Idaho had about 1.5 times 10 to the 6th power people in 2007, how many potato chips would Idaho residents have consumed in 2007? Without using a calculator, make an exact computation and record your answer in scientific notation. You're just going to ignore that piece for now. Oh, yeah. Okay. So it starts out that we have this many potato chips eaten by each person and then this many people. So to find their total amount that they would eat, that'd be multiplying the two. So I'm going to write 7.4 times 10 to the 3rd power times a quantity of 1.5 times 10 to the 6th power. So from there, group-like terms, I'm going to do 7.4 times 1.5, and that's going to give me 11.1 times 10, and then when we're multiplying bases with exponents, we actually add the exponents. 6 plus 3, that's my 9. Again, we would be done, but this is bigger than 10, so we have to change it back to scientific notation. This piece just only right there would be 1.11 times 10 to the 1st power. And again, if you think about this, if you take this number and multiply it by 10, it makes it bigger by one place value, and you would end up back with that number. So this is the same as just that piece. But continue with this piece here. Can't get rid of that. It was always there before. And combine 1.11 times 10 to the, and when we're multiplying bases with exponents, we actually add the exponents, 1 plus 9, 10. And there it is. All right, last one. Ooh, the pyramids. One of the giant pyramids of Egypt is made of about 2.4 times 10. Wow, that's bouncy. 10 to the 6th power carved blocks of stone. If each block weighs approximately 4.95 times 10 to the 3rd pounds, how many pounds of blocks would make up the pyramid? So, wow, that's a lot. We're going to multiply these out. And so we're going to write that out. 2.4 times 10 to the 6th power times 4.95 times 10 to the 3rd power. Again, multiply the things out that I can, just the regular old numbers. That's going to give me 11.88 times 10. And when we're multiplying bases with exponents, we actually add those exponents. 6 plus 3, that's my 9. Once again, third time in a row, this is not in scientific notation. It's bigger than 10, so we're going to write it as, instead, 1.188 times 10 to the 1st power. Notice if you take this number and multiply it by 10, you get 11.88. So this number is the same thing as this. Bring down the part that we haven't used yet, but we still need. And that's going to leave us with 1.188 times 10 to the 10th power. Are you tired of me saying this yet? Because when you're multiplying bases with exponents, you actually add the exponents. And 1 plus 9 is 10. All right, so there it is, folks, using scientific notation.